All right, let's talk about Hamilton paths and Hamilton circuits. Previously, we discussed Euler paths and Euler circuits. If you switch the word edge in the definition of Euler circuit with vertex, that gives you the definition of a Hamilton circuit. So, a path that passes through each vertex of a graph exactly once is a Hamilton path. And then if you have a Hamilton path that ends at the same vertex you start with, that's a Hamilton circuit. So what we're going to do is, for the first few examples, we're just going to work through these examples trying to find Hamilton paths and Hamilton circuits. Unfortunately, there is no analog or equivalent to Euler theorem that we can use for Hamilton paths and Hamilton circuits. Okay. So I've got some examples we're going to look at. Here it says to find the Hamilton path in the given graph. So for a Hamilton path, we want to hit every vertex exactly once. And in some cases, they'll tell you a particular vertex to start with. In this case, we're really limited to which vertices we could start with. So, like I said, we want to hit every single vertex. If I start at A, and I go to B and then D, well, at some point I have to try to get back to C. So then I guess if I start at A and I go to D and then B and then C, I can't get back to B to finish this out. So really, you can think about C and F as your endpoints. So what I'm going to do is I'm going to try that. I'm going to start with C, and then I'll go to B. As I do this, I typically will use my highlighter to trace it out. So C to B. All right, at this point, I have two options, A or D. Well, if I want to hit every vertex, I have to go to A, because if I were to go to D and then A, so we're trying to hit every vertex exactly once. So if I were to go to D and then A, I'd have to hit B again. And so I could maybe cover all the edges, but I really only want to cover all the vertices. So from B, I'm going to go to A, and then from A, I'll go to D, and then you probably see the rest. And then I have to go E and then F. Okay. E, F. C, B, A, D, E, F. Or you could go the opposite way, which would be F, E, D, I'm just going backwards, A, B, C, A, B, C. So think of those as endpoints. I have to end on one of those because I can't retrace over it. All right, so the next one, number 2, says find a Hamilton circuit for the given graph. And I want to squeeze in here beginning at vertex A. We have several options, and so in the homework, they're usually going to tell you where to start if you have lots of options. Here, we're going to start at A. We want to hit every vertex once. So let's see. A to B. Now, the problem here is if I were to cross over here to C and then do D, E, then I hit B again and come back to A, then I violated the definition. I can only hit every vertex once. So if I go to B, I have to go to E, and then D, and then C, and then A. Okay, so A, B, E, D, C, A. And you can see A, B, E, D, C, A. And I could go the opposite way. If I go from A to C, again, if I were to cross over to B and go to D and then E, I still have to cross back to B. Or if I went from C to B and went to E, I'd still have to cross back over C. So A, C, D, E, B, A. So both of those answers are acceptable on the homework. All right, we'll look at a couple of more examples before we learn something new. Here we want to find a Hamilton path and circuit, if possible, for the following graph. Okay. So in this case, I've introduced a bridge, which we've had bridges before, but here we've got what they call this the dog bone example. It kind of looks like a dog bone or a bow tie. But this kind of plays a big role here, this bridge. So if I want to create a Hamilton path or circuit, I really can't start at C or D. I have to start at these endpoints, well, these pieces here. So let's just start with A, and we'll just see what happens. All right, well, I don't want to go A to C, because then I'll go to B, but I can't get back to C. So I really want to, for this example, go to B, and now I can go to C. All right. Once we've crossed to C, well, you have no choice to go to D. And then at this point, you could hit either E or F, and then the other. So A, B, C, D, E, F. So that's just one option. There's several. I don't even know if I'm going to give you all of them. I could have gone A, B, C, D, A, B, C, D, F, E. I could have also gone, well, probably going to run out of room here, but I could have gone B, A, C, D, E, F. Now I don't even have to start on this side. I could have started on this side, so I could have done F, E, D, C, B, A. And I'm just going to write etc. But I think hopefully you understand what's going on here. Okay, so there's a few more you could come up with. So is that a Hamilton path, Hamilton circuit? Turns out there's no Hamilton circuit possible, but several Hamilton paths. Okay. So for this next example, I haven't completed it. I wanted to kind of show you what I'm doing for this graph that I'm going to make. All of the vertices on top are going to be connected to the vertices on bottom. So for instance, after we do this, it's going to look like a spider web. So A is connected to each of the ones on the bottom, B is connected to each of the ones on the bottom, and C is connected to each on the bottom. So I like to always draw this one out in class. And then you're also going to notice that the vertices on top are not adjacent to each other. I mean, they are I guess, close to each other, but they're not adjacent. And then, of course, C, we'll play the same game. All right, so for this example, so you see it looks like a spider web. So it's a little easier to explain if you just explain that the top vertices are adjacent to the bottom ones and the bottom ones are adjacent to the top ones, and that's it. So it says find a Hamilton path and circuit, Hamilton circuit for the following graph, if possible. So here they didn't tell us where to start. It won't matter. I'm just going to start. I always kind of like to start at an endpoint if I have no idea. So since it seems like there's more vertices on the bottom, I'm going to start at D. Try to start at a different one, see if you also can do this. All right. I am not connected to E, F, or G, so I have to go to A, B, or C. To avoid any type of confusion, I think I'm going to just start at the left and keep going to the right. But if this doesn't work, you could try something else. So now I'll go to E. From E, I'll go to B. Again, this is one possibility. You could try something else. B to F. I have to go to C next. I've hit all the top vertices. And then from C, I have to go to G. Well, problem is we started at A. No, we started at D. Okay. If it is a circuit, I end on D. Well, if my next stop would have to be B, but I can't hit the same vertex twice. And so what's going to happen is I am not going to have a Hamilton circuit. So there's no Hamilton circuit, but it appears to be a Hamilton path because we hit all of the vertices, D, A, E, B, F, C, G. I'm not able to get back to D, so it's a Hamilton path. Okay, but not a circuit. All right, so for the next bit of information, we need to talk about the difference between complete graphs and not complete graphs. So again, I've left these kind of blank. So some graphs, however, always have a Hamilton circuit. This guy did not have a circuit. A complete graph is a graph that has an edge between each pair of vertices. Okay. So again, I wanted to draw these in real time just to show you. We're going to see this picture again. So if a graph is complete, then that means each vertex is connected or adjacent to every other vertex. So this picture will be familiar. You'll see a lot of these in the homework. To construct it, I start with my vertex A or whatever's first, and then I connect it to all of the other vertices. Okay, now I'll do B. B is now connected to A, connected to C, now D, and then E. So now move to C. C is connected to A and B, and now D. Then E. And then D is connected to A, B, C, E. Okay, so it makes this shape, this pentagon, the star inside the pentagon shape. All right, so this guy is complete. Each of the vertices are connected or adjacent to the rest of them. Now, this one, I will intentionally make it not complete, and I'll explain why. So this one is not complete because, for instance, A and D doesn't have an edge. So this one is complete. This one is not complete. Also, A is not connected to E. B is not adjacent to D. We could add some vertices to fix this, but I just wanted to show you what's a complete graph, what's not a complete graph. Now, forget about this guy for a second. Here it says how many Hamilton circuits exist for the complete graph. By complete graph, we mean this guy. If we begin at vertex A. So we're about to figure that out together. So, how many Hamilton circuits exist for complete graph if we start at A? So I start at A. Keep in mind, I'm only allowed to hit each vertex once. So I'm going to start at A. Actually, let me do it this way. We want to figure out how many. So let me do this. I'm going to treat this as a blank problem. I may need to add more blanks, so forgive me. But we're going to start at A, and then we have first stop, second stop, third stop, etc. So if we start at A, for my first stop, I could go to B, C, D, or E. That's 4 options. Okay, let's just do that. Doesn't matter. I'm going to just go to C. From C, for my next stop, I could either go to B, D, or E. So I have 3 options. So let's go to one of those. I'll just go to D. Now that we're here, I can go to D or E. So you probably see the pattern that's emerging. So let's say from B I go to E. Well, I'll say let's go to D. It doesn't. And then, of course, once we're at D, we have to go to E. We have to end up at A. Okay. 1, A, C, B, D, E, A. Okay. So that means, and we could have done several different things, right? But notice this pattern that should be familiar to you. All right, so that is equal to 4 factorial, of course, which is 24. But that's the important part. So turns out that this pattern we just discovered is true for all of these. So we had 5 vertices, and we ended up with 4 factorial Hamilton circuits. It's a complete graph. So if you have n vertices, means you have n minus 1 factorial Hamilton circuits. So let's look at a couple of examples that I found that's going to use that. So find the number of Hamilton circuits for a complete graph with 12 vertices. So again, remember, that if you have n vertices, you have n minus 1 factorial Hamilton circuits. Okay, we're going to use that. Here we have 12 vertices. So that's 12 minus 1 factorial, which is 11 factorial. That's a huge number. 11 factorial is 39916,800. 39916,800. Hamilton circuits. Example 2 changes it, makes it backwards. We know that we have 720 Hamilton circuits, and they want to know how many vertices that we have. So, what kind of number is 720? Well, we know that whatever this number is, the number of Hamilton circuits, is a factorial of something. Okay? Let's make that note. We know the number of Hamilton circuits is a factorial of something. And I don't really like trial and error, but this is about where we're going to use trial and error. Now, with enough experience with doing factorials, you might remember what this is. But let's say you don't know. So what we can do is we know that, well, you should know that 3 factorial is 6. So I'm going to start with 4 factorial. So 4 factorial is 24. All right, it's not a 4 factorial. Let's try 5 factorial. That's 120. We're getting closer. Let's try 6 factorial. I don't know if it's going to work. Oops. Oh, there it is. So 720 is 6 factorial. So let's figure this out. So 6 factorial is 720. So that is 7 minus 1, because 6 is just 7 minus 1. And so this number here is our n. So n equals 7, which means it had 7 vertices. Okay, so you'll have to try that. So my advice is just keep practicing that. It'll come better. It'll come natural eventually. But this one is the harder one. So if you see that in the homework, you may need to practice it a few times. All right, so this brings us up to the last section, last grouping of questions. We're going to talk about weighted graphs and the traveling salesperson problem. So, a graph whose edges have numbers attached to them is called a weighted graph. The numbers shown along or attached to the edges of a weighted graph are called the weights. So basically down here I have some numbers. Those red numbers are weights. That could represent cost or time, usually aspects of business that we want to minimize so we can spend less money or save time. We have 2 ways to do it. We have the traveling, well, no, before we get to that, we have the traveling salesperson problem, which is finding a Hamilton circuit in a complete graph in which the sum of weights is minimized. So such a circuit is called the optimal solution. Okay, and we have 2 methods to do that. We have brute force, which we'll talk about on this page, and then we have nearest neighbor, which we'll talk about next. So for brute force, it's probably the hardest one because it requires us to do a lot of work. And if that's the case, then we're probably going to only have a graph with like 4 or 5 vertices. And you'll see why as we get through this. Okay? So, we got an example down here. We're going to use brute force to find the optimal solution. But here are the steps. We're going to create a graph if it's not given. Generally, you see a graph in the homework. Sometimes they tell you a story that you're maybe taking some doing some errands, and you have to go to the hospital, the post office, or whatever. And then you create the graph yourself. Here, I've already given it to you. You make a list of all possible Hamilton circuits. Well, how many Hamilton circuits do we have? Here we have 4 vertices. So 4 vertices, which means we have 4 minus 1 equals 3 factorial, which is 6 Hamilton circuits. That's not so bad. We only have 6 Hamilton circuits. That's not bad. If we had 5 vertices, that is 24 possible Hamilton circuits. That's a lot. So let's make a list. I usually do a table. So this. So here's going to be my Hamilton circuits. We're going to say starting at A, otherwise, and they'll do that, starting with A. They usually tell you where to start, so I should have included that. So I'm going to do that first. We're going to come up with all our Hamilton circuits, starting with A. Okay. So I could go A, B, C, D. Back to A. A, B, C, D, E, A. Let's say I start with something besides A. Let's say instead of going to B, I went to C first. I think I'm going to do that. So I'll go A, C. I'll tell you what. I'm changing it again. I want to go A, B, C, D, A. We did that first. Let's go to B second and do the other possibility. A, B, D, C, A. A, B, D, C, A. Why am I doing this? Well, I got to come up with 6 of these Hamilton circuits, and you may find a way that works best for you. For me, it's taking the first stop and then changing the second stop, and then I'll do that again. I'll do, instead of starting with B, let's start with C, and I can do A, C, B, D, A. A, C, B, D, A. If I stick with starting with C, A, C, D, B, A. We're almost done. We only have 6. So, I did both cases with C second. Now I'll have to do D second. So A, D, B, C, A. A, D, B, C, A. And then lastly, A, D, C, B, A. All right. That's all of my possible Hamilton circuits. But we got to come up with the most efficient one. So I'll warn you, this is probably the longest type of question in this section. So what we're going to do is add up all of these, and I'm going to just draw it for the first one. So we went A to B, and then B to C, and then C to D, and then D to A. And we're going to get the total there. So 27 plus 14 plus 44 plus 50 is 135. I would probably do these calculations twice because you would hate to miss such a small part of the question. All right, now let's do AB, D, C, A. Oh, I need a value here. This value is 30 plus 30. So I did 27 plus 25 plus 44 plus 30. And that's 126. All right, let's try this next one. Now we're going to go AC. So AC is 30 plus, so AC plus B, C to B is 14. B to D is 25. Plus D to A is 50. Double check that. A to C is 30, C to B is 14, B to D is 25, and then 50. I don't think this one's going to be the smallest. Okay. Oh, it might be 119. All right. Let's go one more time and see if we see a pattern. So AC is 30, CD is 44, so AC is 30, CD is 44, DB is 25, and then BA is 27. Got 129. I'm thinking there's a mistake somewhere. I should be seeing some repeats. So ACDBA, ACDBA, it should be the same as this. So let me double check, make sure I did this correct. 27 plus 25 plus 44 plus 30. That's correct. Let me double check this. Oh, I think I know what I did wrong. I think I did 33 instead of 30. Yeah, so this is a 126. All right, so yeah, you see these guys start repeating. So let's see, A, C, B, D, A. A, C, B, D, A is this one. And then A, D, C, B, A is this one. So if you want to write out those values, you can, but you'll notice that you get the reciprocal or the inverses, and these numbers are the same. So our best solution, the smallest solution, is actually 2 of them, and that's going to happen. So you have 2 optimal solutions. In this case, ACBDA and ADBCA, same thing. And so they both yield 119. And that's going to be true. A lot of times you will have 2 answers. All right. And now we have one final example, and that'll wrap up this section. Well, it's the nearest neighbor. The good news is this is a lot easier than brute force. And so we have a little bit of a larger graph, but with the nearest neighbor method, it's a lot easier. So, create a graph if it's not given. Oh, by the way, this one gives you the best approximate solution. May not always be the best, but sometimes close enough is good enough. Create a weighted graph if it's not given. Here we got a graph. Identify a starting point vertex. In this example, we're going to start with C. Usually the homework's going to tell you that. From a starting point, this is the easy part. From a starting point, choose the edge with the smallest weight. And you're going to keep doing this. You keep doing this until you've hit every single vertex. So from the second vertex, choose the edge with the smallest weight that does not lead to a vertex already visited. And we keep doing this, realizing we have fewer and fewer stops until we end back at C. So what I'm going to do is I will start with C. I'm going to highlight my path, and then I'll add those values up. Generally, they'll ask you to write out the path and then also give the value, the total weight. All right, so we just look at these numbers. 3, 10, 19, 7. Well, 3 is the shortest. Okay. So the first time I had 4 stops. Now I've only got 3 stops. Now we start over. 12, 8, 15. Well, 8 is the shorter one. And the further we go, the easier it gets because we have fewer and fewer stops along the way. We can't go to C. At this point, I can either go to E or B. 9 versus 3. And then we have to go to E. And then from E, we can return to C. C, D, A, B, E, C. All right. So now we'll come up with the total. The total, let's see, CD is 3. D to A is 8. A to B is 3, B to E is 4, and B to C is 10. So let's total these. 28. All right, and there we go.